Hello everyone, this is Swapnadeep from the UK, and today in this talk I'll be talking about our recent ongoing investigations on wind effects on wave overtopping at vertical coastal defenses. This is a collaborative work between Environment Agency, EDF Energy, Torbay Council, Royal Haskoning DHV, HR Wallingford, and the Manchester Metropolitan University, where I joined the computational modeling group as a research associate. I'm presenting this work on behalf of my supervisor, Dr. Jian Zhou. The motivation for this study is linked with the global climate change. Catastrophic events like storm surges are expected to occur at more frequent rates due to sea level rise. Many of these events are characterized by very high wind speed, and if there is a transport link passing by the coastal defense, there is a greater hazard due to the increase in this wind speed. Many of our existing coastal defense infrastructure are not capable to face with these challenges, and we don't get deterministic answers for very basic questions like what is the increase in the overtopping rates due to the increase in the wind speed from state-of-the-art coastal engineering. So some of the similar questions we try to address in this study. Our primary aim is to come up with a comprehensive database that our industrial partners can use to understand wind effects on wave overtopping, and in order to achieve that, we conduct complementary numerical and physical model tests. The numerical model is based on two-phase CFD solver based on open source model OpenFOAM, and the computational domain, as we see in this slide, consists of a constant water depth region where we try to achieve the desired wave conditions by proper boundary conditions at the inlet. There is a fixed structure at the top of a sloping beach mimicking the coastal defense, and there is a narrow wind zone close to the coastal defense through where we try to import the desired wind field in our domain. The governing equation behind this model is essentially the continuity and the Reynolds average Navier-Stokes momentum conservation equations coupled with a volume of fluid methodology to track the free surface. We have additional pressure gradient corrections on this momentum conservation equation through which we import the desired wind field in our domain. This correction is cell averaged to maintain the numerical stability. We don't include turbulence in our model, and therefore we are not able to understand what is the effects of the wind on the wave run-up on sloping beach. The preliminary study we adopt to validate our simulations is from by Ward et al., and they presented this result a few decades ago in this very coastal engineering conference. On the video on the left, we saw the velocity in the wind field, where you can see the zone in red is actually the region in the air phase where the speed is same as what is given as input wind speed. On the video on the middle, we saw the evolution of the free surface during the wave interactions with the coastal defense, as you can see in the presence of a wind speed, how it is completely carried away on the other side of the coastal defense. On the plot, on the rightmost side, we look at the overtopping rates under different incident wave conditions and under two different wind speeds. So from this plot, you can clearly see our calculations matches very well with that measured by the physical model tests by Ward et al. And secondly, the wind effects are higher at smaller incident wave heights. By the time we are developing this model, our partners at HR Wallingford were involved in planning the physical model tests. The plan of the bathymetry of the flume, where we try to achieve the desired shallow water condition, is shown in this plot. There are several wave gauges, and gauges from 2 to 6 is most vital because from our point of view, because readings from those gauges we use as model input when we try to replicate the physical model tests in our numerical simulations. Excuse me. This is the plan of the structure we use in the physical model tests as in the prototype scale to model the coastal defense. And we have tanks with many partitions after the coastal defense. There are many dipsticks inside those partitions through which we monitor the increase in the water level during the overtopping events. And from this data, we are able to calculate the overtopping rates cycle-wise. And secondly, from the same set of data, we can also calculate what is the distribution of the overtopping discharges as we get away from the coastal structure. For the tests with wind, we use 2 rows of fans just a few meters before the coastal defense. The power input to those fans are controlled through the use of wind dial gauges. The calibration between the readings of the wind dial gauges and the actual wind speed we achieve near the coastal defense is achieved through the use of anemometers. To be most realistic, we use broadband irregular waves where we vary the incident spectral wave height and peak wave periods over a range of offshore still water depth. sample input and output of the overtopping rates that we can calculate using the dipsticks in the physical model tests is shown in this table. This is the model input spectra that we can use in our numerical model. And since we are using active wave absorption in our numerical model, we can use much smaller computational domain, and therefore we can run our simulation for sufficiently long time to get statistically significant results. So one of the key sources through which we can best understood of the wind effects on wave overtopping is perhaps the impulse parameter, which is given in terms of local water depth at the coastal defense and incident spectral wave parameters. So it is interesting to see that for the same impulse parameter, we get characteristic high overshoot in the physical model test, as well as in the numerical model based on OpenFOAM, and then in the shallow water model SWAS, which is much used in coastal engineering. We can superimpose the impulse parameter in the incident wave parameter space, where the thin continuous line represents the impulse parameter for which its value is 0.23. So there are several points in this plot which represents the various data points we use in our database, and the points on the concave side of this line are characterized by very high overshoot. So only these 3 points you can see in red, black, and cyan. Now we'll consider in a couple of few next slides to best understand the results from our numerical simulations. These 3 points represents 3 different incident wave heights. So if we study the non-standing wave instability, this also gives better insight of the impulse conditions at the coastal defense. So this is preliminarily studied by Longboard, Higgins, and Drazend, and they found there is a critical wave stiffness between 0.25 to 85 to 0.44, where the nonlinear effects during the wave interactions with the coastal defense are most dominant. So now if you look at the wave elevation time history measured at the coastal defense, we can see when we are inside the critical wave stiffness, we have something called triplets. And then if we look at the free surface evolution during the overtopping, we can see during the triplets, the third wave is much steeper and much thinner compared with preceding wave cycles. But whereas when you are outside this critical wave stiffness, we don't have these differences. This gives findings become very useful if we try to plot the factorial increase in the overtopping rates in the presence of wind over the normal windless condition over Reynolds number based on local wind speed and thickness of the overshooting jet at the instant of overtopping. So lower wind speed does not have sufficient kinetic energy to alter the overshooting jets, but when the overshooting jet is thin, that may be resulted due to the impulse type conditions. They can be very easily affected by low to moderate wind speeds. So this gives us actually practically very small wind effects at smaller smaller wave stiffness, and as we increase the wave stiffness, the overtopping during a normal windless condition decreases. So this is something quite peculiar. We can also verify from the Bennett GP online tool developed by HR Wallingford based on numerous data from field campaigns. But in the presence of wind, even with the increase in the wave stiffness, we can have increase in the overtopping rates. So this is quite drastically two different pictures in wind, in the overtopping with wind compared to overtopping without wind. So this is just a comparison between our model and the physical model test in terms of the distribution of the discharge as you go out from the coastal structure, and close to the coastal structure, the flow is very much dominated by the mixing. So this is some data we can gather from our physical model test and then come up with this kind of variation of the overtopping, non-dimensionalized overtopping rates over range, where we change the freeboard of the coastal defense and the incident wave spectral wave heights systematically. So there are a couple of regions in this plot. On the higher incident wave height, the wind effects are quite small, whereas in this smaller incident wave height, the wind effects are much higher. But somewhere in between, there are obviously some uncertain region where the wind effects are also quite significant. But on average, we can say with the wind effects gets higher as we decrease the incident wave height. And this is something quite close we can verify from our simulations and the past study by the Ward et al. So lastly, we apply our developed CFD model to an engineering application where we model the storm Emma, which lashed over the Torbay coast on first week of March 2018. And very high wind speed and significant wave height we recorded in this event. And then we set up our OpenFOAM to model this event. So then if we run our simulations with wind of around 20 meters per second, which is quite close to what we experienced from this event, we can see our simulations are quite close to the actual footage that we take during this event. So this is lastly just a small demo of the graphical user interface, which links the user's request with the database we are developing. So this database is not very comprehensive yet, but it has a fair range of input parameters that the user can choose to understand the wind effects on the overtopping discharges. So in summary, we would like to conclude that we found that thinner overshooting jets are most prone to wind effects, and this type of thin overshooting jets can be resulted even during impulse type wave interactions from a smaller incident wave heights. But we believe that if the overshooting jet is very thick and the wind speed is also very high, then the overshooting jet can also be similarly sensitive to the wind speed. In our physical model tests, we have not been able to achieve this very high wind speed, but we believe the dynamics of those wind interaction with the thick overshooting jet will be quite different from what we achieve in this study. We also need additional capabilities to handle mixing in our numerical domain. So this is the project which is duly funded by the Natural Environment Research Council and CELIA, to whom we are most grateful. We have also received key input and support from other NARC-funded projects that is led and conducted by the Natural Oceanographic Center at Liverpool. So thank you very much for giving us this opportunity to present our ongoing work on this virtual coastal engineering conference.